Yeah, we can start.
Okay.
Okay. I don't think that Chiara really needs an introduction, but since he is recorded, I think that he's safe for the one that will watch this video later. Chiara is with us for a few months by now, and she's a PhD student in the Quantum AI PhD course, and she will speak about work during the master, right?
Yeah. Can I start? Okay. Okay. Hi, everyone. Today I'm gonna talk about the work that I did during my master thesis at University of Pisa. The work focused on the three-qubit quantum refrigerator, and that combines theory and proof of principle implementation on IBM quantum hardware. And it was supervised by Michele Campisi, Lindsay Bassman, and Davide Rossini.
This is the done. Well.
Okay. The outline of the project, the first thing that I did was the model of the three-qubit quantum refrigerator. Then I found a maximal cooling protocol via a unitary evolution. Then the most general form of this unitary evolution that is also the one that minimizes the cost in terms of work. This model and this protocol was implemented on an IBM quantum computer after a circuit optimization that aims to reduce noise. Last, I did a study on the role of correlations and dissipation and how they impact the performance of the protocol. So the model is really simple. We have a bipartite system that is made up of a cold subsystem and a hot subsystem. The cold subsystem is 1 qubit at temperature T cold, and the hot subsystem is made up of 2 qubits, 2 and 3, temperature T hot. All the 3 qubits share the same frequencies, and they are all initialized in a thermal state. So that the initial state of the bipartite system is the tensor product of the 2 subsystem Gibbs state. So we can see this as a 2-stroke engine, where in the first stroke we have the whole system undergoing an external driving Vt that is time dependent, and it implies a unitary evolution. After the driving is turned off at time tau, we have the second stroke in which the 2 subsystems are let thermalize again with the respective beds, and they go back to their initial temperature, Tc and Th. So this, the cycle can start again. Okay. The goal of this is to cool qubit 1 at expenses of qubit 2 and 3. So our goal is to find the unitary U that minimize the final cold subsystem energy that is given by the trace of its Hamiltonian and the evolved states. To solve this minimization problem, we exploit the concept of ergotropy that was first introduced by Alaverdian et al. In 2004. So ergotropy is the maximum work extractable from a quantum system via a unitary cyclic evolution. So our problem is the same, but in ergotropy we address for the total system energy, and here we address only on the cold subsystem energy, so the energy of the qubit 1. So we borrow the technique used in the ergotropy problem, and in particular we noticed that the Hamiltonian commute with the initial state. So in this case was found by Alaverdian in this paper that the unitary evolution should be a permutation that maps the eigenstate of the rho with the highest eigenvalue to the eigenstate of the Hamiltonian with the lowest eigenvalue, and so on with the second highest eigenvalues of the rho with the second lowest eigenvalue of the Hamiltonian. And so the unitary is a permutation that maps, in our case, the first 4 half of the state that have the lowest energy with the half of the state that have the highest population. So we order the eigenvalues of the rho in a non-increasing fashion. So the unitary performs a permutation sigma that remap the eigenenergy in a decreasing fashion. So we find 2 range of temperature. One is this, where if we look at all 8 states in lexicographic order, where the first one is the cold qubit and the other 2 are the hot ones, we see that the energies are already ordered in a increasing fashion, and to reorder the population, we have just to swap the state 0, 1, 1 and 1, 0, 0. So the unitary that implement this is just a swap of these 2 states. In the other range of temperature, we already have the right ordering, so no cooling is possible. This is the form of the unitary metric that swap the 2 states here. And if we go back, we can see that we have a high degeneracy, both in the energy and in the population. In particular, we see that these 2 states and these other 2 share the same population and the same energies. So we can apply any unitary transformation within their subspaces, and this will not affect the cooling protocol. So this is the most general form of this unitary operator with general rotation in the generated subspaces. So we have 3 parameters for the 2 rotations and all the 4 phases parameters. So we have 12 free parameters that whatever we choose will obtain an optimal unitary that implement the cooling. After this unitary operation, we can also apply a permutation, because here we see that the first 4 states and the other 4 share the same energy, so we can permute these 4 and these 4, independently. And in this case, also the cooling remained the same because we have the same evolved final states. We repeat the same protocol, but now we want to find the minimal cost in terms of work. So we apply again the ergotropy problem, but now we use the total system energy. And we see that in this case, the energies are already ordered in a increasing fashion and the population in a decreasing fashion. So the unitary that we found before, this one, without any permutation, it's also the one that implements the minimal cost in terms of work. So in the other studies, we're going to use this one without any other permutations. Okay, so we calculate the average variation of the cold qubit energy, and we plot in the with temperature, hot and cold, and we see that it's always negative as we wanted. So it means that the system actually cooled down, and it's maximum when the two initial temperatures are closer. Then we see how adding a general permutation after the unitary affect the cooling and the work. Arrivederci. So the the cooling will remain unchanged, but the work and the variation of the energy of the hot subsystem will change, because the other one was the one with the minimal work cost. So if we plot the average work without the permutation and with the permutation, we see that we have one order of magnitude in which, in this case, is higher. Then I implemented this protocol on an IBM quantum computer. So the first step was to prepare the initial state in a Gibbs state, then transpile the unitary evolution into a quantum circuit, and then optimize this circuit in order to minimize the number of 2-qubit gates that are the one more prone to noise. So it's not possible to initialize a state in a Gibbs state on a quantum computer. So we use these other methods in which we create 8 different circuits, each of them initializing one of the possible base states of the 3-qubit system. Then apply the unitary evolution to each of them independently, and perform a measurement in the computational basis. So the measurement output is these are the counts of obtaining output J given output E. So the conditional probability of J given I is given by the counts divided the number of measurements, so the number of shots on the quantum computer. And to obtain the actual Gibbs probability, we reweight those conditional probability by the respective Gibbs weight. After that, we have seen that in the unitary matrix, in the most general form, we have 12 free parameters. So we do an optimization to find the set of parameters that minimize the number of ECR gates that are that were actually the 2-qubit gates on the IBM quantum computer. So we see that the minimum number of these gates is 8, and we don't have just one set of parameters, but we have multiple minima. And this is the circuit after the transpilation and the optimization. So we have 8 ECR, and here we set all the phases to 0. Then from the relation between the temperature and the population of the excited state, we find the final temperature of the cold subsystem. And we plot here with respect to the temperature, the implementation on the IBM Brisbane and the simulation with the an ideal quantum simulator. And we see that in the ideal case, the variation of the temperature, so it's always negative, as we expected. But in the implementation case, the cooling is only possible above this line, and it's due to the noise inherent to the quantum simulator. Actually, IBM Brisbane was retired some months ago, so I tried to implement it on the IBM Marrakesh that has a better processor and a different basis gate. And we see that the cooling actually works better because we have a wider range of temperature in which it actually works. And here I didn't redo the optimization, so there is a chance that it could actually work even better. And last, I studied the role of correlation and dissipation in this system. So was first studied in this paper the multipartite system in contact with many bands. We have that the total dissipation consists of 2 terms. The first one is the individual lengths, so the distance between the state and this respective equilibrium state, and the correlation that in the case of bipartite system are given by the mutual information. So we define this ratio between the correlation and the total legs. So the bigger would be this ratio, the bigger the importance of correlation in the system. So first, I try to see how this correlation impacts the protocol using general unitary evolution dependent on two parameters, and is made of a partial Toffoli gate that acts on these two states and a partial swap on these two states. And it's just a general unitary evolution that generates correlation in the system. And first, we fix the cold qubit energy variation, and we see how the coefficient of performance scales, and this ratio at the same fixed energy. And then we fix the efficiency of the coefficient of performance, and we see the energy variation of the cold subsystem and also this ratio. And we see that when this ratio is maximum, so correlation are stronger than the lags, than the dissipation, the efficiency is maximum. But in this other case, we see that when this ratio is maximum, the cooling it's lower. So we can say that in general, correlation are not always detrimental, but we can see that in this case, when we have higher correlation, we also have higher efficiency. Here, higher correlation, lower cooling. So in general, they're not always a cost, but it depends on what we are looking. If we are looking at the efficiency or the energy variation, so the cooling. Then I look at the same quantities, but reconstructing the total final density matrix via quantum state tomography. So we see how the correlation that builds up during the implementation on the quantum hardware affect the performance. And we see that here, at fixed variation of the cold subsystem energy, we have the maximum of this ratio and the minimum of the efficiency, and also at fixed efficiency, the maximum of the ratio corresponding to the minimum of the cooling. So in this case, it looks like they are always detrimental for the performance, but it's only restricted to this temperature range. So it's always an open question if in other temperature range or in other situation, the correlation can be used to boost the performance of the cooling protocol. So to conclude, we have found the most general form of the unitary transformation that achieve maximal cooling and also the minimal cost in terms of work. The cooling was demonstrated on a quantum computer, but only within a specific range of temperature, but with some limitation due to near-term quantum devices. And we have demonstrated this dual role of correlation in the cooling performance. Some outlook can be scaling to larger system, but I think it was already done in this article. Integrating some error mitigation techniques to reduce noise in the quantum hardware, and relax some optimality constraint. That it means we can not use the unitary that implement the maximal cooling and the minimal cost in terms of work, and maybe it will go in a circuit that is less noisy and maybe implement better performance. So, thank you for the attention.
The equivalent of a free energy classical.
Yeah, it's the
free energy is just the superior limit of this some constraint, some relation.
Yeah, I think so, because the ergotropy is the maximum work extractable. The same of the free energy.
There is something like the second question is in the first or second slide you show there is one qubit called two-qubit red. The question is
here.
Yes.
Mm-hmm.
These qubits are just equal or okay. These are you consider two because you can extract much more.
One cold and one hot is not possible to extract, and even in the case in which I have two cold and one hot is not possible. I didn't try any other with.
There is interaction.
Yeah.
Okay, and then you can extract much.
I mean.
From okay.
Okay.
Go back to the slide with the state operation. I really understood the this one.
Okay. I create 8 different circuits, all independent.
Each run you prepare one possible circuit.
No, I prepare on 0, 0, 0, 0, 1, 0, 0, 1, and so on with all 8 states. Then apply the unitary circuit to each of them, measure, and I obtain the counts. Then I normalize by the number of measurements and multiply by the Gibbs weight. So
and is equivalent to prepare the state on.
yeah, the probability at the end matches.
This the usual trick that they do when they come. Okay, say the and then we mix up.
I think there are more precise methods, but this is what the simplest. Before that?
I think it's like
Hmm?
So, as I said, you do measurements plus
Sorry, I didn't hear.
Use like a single protocol where you measure like the maximum work expression you can do just one out of the.
No, multiple runs.
And you measure. So it's basically a point measurement.
Yeah.
Right?
It's like the 2-point measurement scheme. Yeah.
So you when you were about correlations, so the correlation is you.
During the protocol.
Chiara, you look into the fact of forms of correlations?
In general, classical and quantum.
You don't know
No, I look correlation in general.
And then I have another question related to, at some point you referred to the by Jake Shred and cooled down by many others. My understanding, yeah, that one. My understanding of that paper, again, but my understanding of that paper is that these are exotic form of sympathetic.
Okay.
You pull a bunch of things, and then you also, if you have your freezer, you put your chicken inside the freezer. Right? So
Okay.
it's sympathetic cooling. What you have done is not that. So,
Yeah.
So you are not cooling. So your performance of cooling, performance is not dictated by the fact that you have all the systems.
No.
So how would you link the two?
I don't know actually. I thought they do something like algorithmic cool reference.
Which is a form of
yeah, it's okay. It's a little bit different, but I took the idea from dynamic cooling. So
compression of state. You use this volume of state. Okay. There are no more questions. Let's thank again. Yeah.